All right, let's do this thing. We are moving on to lesson number 2. We are solving with inverses. We are going to solve 6 equations, 6 trig equations. We got 2 sine x plus 1 is equal to 0. Sine 2x minus 1 is equal to 0. So now our argument changes a little bit. We got 2 tan sine x plus sine x is equal to tan x plus 1. Okay. 2 cosine squared x minus 5 cosine x plus 2 is equal to 0. Mrs. Contreras, you're not even here and you're crabbing me. Cosine x is equal to 1 plus sine x. And 6 cotan squared 3x plus 7 cosecant 3x is equal to 4. So these problems get progressively more complicated. Let me go ahead and add my name, as we all should whenever we complete an assignment. What is the date? Today is today. Period. Natural numbers. Awesome. The natural numbers don't need the positive symbol. All right, so we are going to solve with inverses. We got a Mrs. Contreras that is frozen in time above us, but boom, she's here to support us. Hopefully she'll be back with us soon. With that said, let's go ahead and get started. Let's not make this video too long. We got 6 equations to solve. So, sine 2x plus 1. Now, when solving trig equations, it's very useful to get the trig function by itself. So what I'm going to do that is subtract 1 on both sides. 2 sine x is equal to negative 1. Divide by 2 on both sides. Sine x is equal to negative 1/2. All right, so our goal is to figure out all angles x that satisfy the following equations. So hopefully you can look at this and kind of figure out 2 angles that satisfy this equation. Let me go ahead and break out my unit circle. I need the y coordinate to be negative 1/2. So here's a unit circle. I need the y coordinate to be negative 1/2. So we got negative 1/2. We have negative root 2 over 2, and we have negative root 3 over 2. Those are kind of the lengths that we're dealing with. These are in magnitude, getting larger as we go down. So we have negative 1/2 right here. Root 3 over 2, comma, negative 1/2. And then knowing this, that's 11 pi over 6. With that said, there are 2 places on the unit circle where the y coordinate is negative 1/2. The other place is over here. I could have drawn that a little bit better. And that is 7 pi over 6. So we have 2 answers. 7 pi over 6 and 11 pi over 6. But we want all the angles. So what are all of the angles that are coterminal with 11 pi over 6? We've done this before. Hopefully this is a piece of cake. Plus 2 pi k. Plus 2 pi k. Awesome. There we go. We've solved 2 sine x plus 1 is equal to 0. We've done problems like these before, especially last unit when we were applying the sine and cosine functions. But we're warming up. We're getting ready for the big punches that are coming later. All right, let's continue. We got sine 2x minus 1 is equal to 0. Now I want you to think about how this problem is different than the previous problem. We have a 1, but the 2, instead of being in the front, instead of being a coefficient, it is now part of the argument of sine. So we're going to have to deal with that 2x after applying the inverse trig operation. Right? The inverse trig operation is this process right here, figuring out which angles on the unit circle give us, and in both of these cases, a y coordinate of something. So, like the last one, we're going to get the trig function by itself. I'm going to add 1 on both sides. But now we are solving for the places where sine is equal to 1. And I believe between 0 and 2 pi, there's only one place that happens. It is when the y coordinate is 1, which is right there. Pi over 2 plus 2 pi k. Right, no other place on the unit circle does the y coordinate equal 1. Down here, it's negative 1. You could also think of the sine function. Not the best. I probably could have scrolled down a little bit. Also not very good. But at pi over 2, we are 1. Anyways, pi over 2 plus 2 pi k is when sine is equal to 1. We don't want when sine is equal to 1. Well, let me take that back. We do want when sine is equal to 1, but that is not the angle we're looking for. Pi over 2 is not the angle we're looking for because we're looking for an angle that when multiplied by 2 gives us pi over 2. How do we do that? We just use algebra rules. We solve for x. Reverse it. Instead of multiplying by 2, let's divide by 2. We're going to get pi over 4 plus 2 pi k divided by 2. That is pi k. Right? Here are all the answers. Pi over 4, if you plug it back in, you're going to get sine of 2 times pi over 4, which is sine of pi over 2, which is 1. 1 minus 1 is 0. Perfect. And if I add pi, I'm going to get 5 pi over 4. 5 pi over 4 times 2 is 10 pi over 4. 10 pi over 4 simplifies to 5 pi over 2. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. That's equal to 1. 1 minus 1 is 0. We have found all the answers. We are solving trig equations, and they're going to get progressively more challenging. So we have solved a generic trig equation, and then we've now solved an equation where the argument is non-x. It's not just x. There's something that's changed about it. Let's proceed. I don't want to take all of your time here, everyone. Ooh. That's nasty. Here's what I'm thinking. The left-hand side looks like it can be factored. Let's factor this thing. Both have a 2 sine x. So 2 sine x times tan x gives me 2 tan sine. And then 2 sine x times 1 gives me 2 sine x. All right, I can redistribute, double check my answer. Ooh, look at that. I have tan x plus 1 on both sides. I want you to think to yourself, is it valid to divide by tan x plus 1 on both sides and kind of just chop, chop, cancel them out? Is that valid? The answer to that question is kind of. If you get rid of tan x plus 1 on both sides, you need to remind yourself that tan x plus 1 might be 0. If I get rid of tan x plus 1, I'm losing information. But if tan x plus 1 just happens to be 0, and there are places where tan x equals negative 1, negative 1 plus 1 is 0. If tan x plus 1 is 0, then whatever 2 sine x is, whatever it is, whatever, written in terrible handwriting, times 0 is equal to 0. So we can't lose the fact that tan x plus 1 is equal to 0. So if you're going to divide by tan x plus 1, that technically is fine, but you need to be careful because if you divide by tan x plus 1 and it is equal to 0, you've lost information. Here's the better way to do it. We've done this before, actually. 2 sine x tan x plus 1 minus tan x plus 1 is equal to 0. Subtract this tan x plus 1 on both sides. Because now I can factor again. 2 sine x, actually let me do it this way. Tan x plus 1 times 2 sine x minus 1 is equal to 0. Look, tan x plus 1 is equal to 0 is one of our solutions. That's that thing that I wrote up here. Be careful. Do not divide by a variable ever. Right, Mrs. Contreras? Boom! Never divide by a variable. If you choose to set it equal to 0, but the better thing is to do is just to move it to the other side and factor. So we got tan x plus 1 is equal to 0, and 2 sine x minus 1 is equal to 0. This is almost the one we did at the front. 2 sine x minus 1, 2 sine x plus 1. Almost the same problem. Not exactly the same problem, though. Okay. Let's subtract 1 on both sides on this one. Let's just go ahead and finish this left-hand equation as well. All right, when is the tangent -1? When are its y and x coordinates opposites? That's going to happen here and here. The same x and the same y, except for their sign. -√2/2, √2/2. √2/2, -√2/2. I've said this many times, but I always use the slope, and the slope is -1 from the origin. The radius is -1 at 3 pi over 4 and 7 pi over 4. So x can be 3 pi over 4. And instead of writing 7 pi over 4, I'm just going to write, I'm going to get rid of this bracket as well. Let's be as concise as possible. 3 pi over 4 plus pi k. Tangents period is pi. Over here on the right, we have 2 sine x minus 1 is equal to 0. Let's add 1, divide by 2. And sine x is equal to 1/2. There's going to be 2 places that are not off by a consistent period. Pi over 6. And I believe it is 5 pi over 6. Plus 2 pi k, plus 2 pi k. Right? That's going to be 2 pi k every single time unless something else is happening inside of the sine function. That's not happening here, though. There are your answers. 3 pi over 4, pi over 6, and 5 pi over 6. And the 3 pi over 4 has multiples of pi. The pi over 6 has multiples of 2 pi. And the 5 pi over 6 is multiple of 2 pi. Right. I'm not going to do it in this video. I'm just not set up to do it. But if you go to Desmos and you graph this left-hand side and you graph the right-hand side, they will intersect at 3 pi over 4 plus pi k and pi over 6 plus 5 and 5 pi over. You know what? I'm just going to do it. Let's just do it. Why not? So we got 2 tan sine x plus 2 sine x. 2 tan x plus, well, I think it's 2 tan x sine x plus 2 sine x is equal to, let me just double check, tan x plus 1. Well, actually, no, what I want to do is I want to do tan x plus 1. And what's it not happy about? Use parentheses around the argument tan x. I'm cool with that. I got you. I'm cool with that, Desmos. Oh, I think it just did it. No, it's still freaking out. Wants it there as well. Okay, so we got crazy intersections happening here. But intersections are happening at, let's just hold over it, pi over 6, 3 pi over 4, and 5 pi over 6. And look at that. Desmos is really nice. It even like holds those points. Pi over 6, 3 pi over 4, and 5 over 6. And then it begins to repeat itself. 3 pi over 4, pi over 6, and 5 pi over 6. Excellent. Let's go back full screen, and let's continue. All right, so you can always check your answers with Desmos. 2 cosine squared x minus 5 cosine x plus 2. You could graph that and see when that graph is 0. See when it intersects the x-axis. But let's solve it algebraically. That's the goal here in this video. All right. Hopefully you're seeing some cool techniques to solve trig equations. What have we got so far? Just some basic ones where we're using the unit circle. We are setting the argument equal to where it needs to be on the unit circle, but then continuing on with some algebra, thus affecting the plus 2 pi k as well. Then we get some factoring techniques. Please don't divide by a variable, and then you're going to get multiple equations that are basically just numbers 1 and number 2. All right, let's continue. We're halfway done. 2 cosine squared x minus 5 cosine x plus 2. Think about it. I encourage you to solve this. Try to solve it. I'm going to proceed in 3, 2, 1. I think Mrs. Contreras would agree that this is secretly a factoring problem. Let's factor it. Right? I'm going to say that cosine x is equal to u, and then replace the cosine x's with u's. The question is, hopefully it factors. Hopefully we don't have to use the quadratic formula. Hint, hint, that might be a thing in the future. I'm so sorry. All right, so let's see. We got the factors of 2 are 1 and 2. 2 and 1 over here, 1 and 2. I could do 2 and 1 over here, but that would be redundant. No need to flip-flop. And I think it's right here. 2 times 2 is 4. 1 times 1 is 1. That's going to give me that 5. 2 u 1 1 u 2. And let's see, I need a negative 5, so I'm going to make both of these negative. Negative u, negative 4u gives me that negative 5u. Negative, negative 1u, yeah, cool. Negative 1 times negative 2 is positive 2. 2 times 2 is positive 2. We are in business. It does factor. Phew. Let's go ahead and sub back in 2 cosine x minus 1. Cosine x minus 2. Oh yeah, I just noticed something that I think you guys are going to enjoy. Let's go ahead and solve this one over here. 2 cosine x minus 1 is equal to 0. Let's go ahead and add that 1. Divide by that 2. Cosine x is equal to 1/2. When is the x coordinate equal to 1/2? That's going to be right here and right here. Pi over 3 and 5 pi over 3. Pi over 3 and 5 pi over 3. Another way you could do it, actually, whenever dealing with cosine, is just plus or minus one of them. That's kind of convenient. Plus or minus pi over 3, because negative pi over 3 is coterminal with 5 pi over 3. They're essentially the same angle. A little bit different. They're straight up different numbers. Don't get me wrong. But they're coterminal. They fall the same spot on the unit circle. They're 2 pi away from each other. Plus 2 pi k. If I add the 2 pi to the negative pi over 3, I get the 5 pi over 3. Sweet. And we got that one. All right, so the other one is, when does cosine x minus 2 equal 0? When does cosine x equal 2? Where on the unit circle, and I'm realizing you guys can't see this because of the pictures of me and Mrs. Contreras. Where on the unit circle, you can see this though, is the x coordinate 2? Well, the x coordinate is 1 there, so 2 is way over here. There is never an x coordinate on the unit circle equal to 2. And if you think about it, if you draw yourself the cosine graph, its range is -1 to 1. Cosine x is never 2. This is what I was saying a second ago, where I was like, oh, I think you guys are going to like this. This does not exist. We are done with that side. No extra work. That's nice. I always enjoy doing that. All right, so when does 2 cosine squared x minus 5 cosine x plus 2 equal 0? Let's actually, I'm struggling with my keyword commands. Let's jump back over to Desmos. Let's figure out 2 cosine squared minus 5 cosine x plus 2. 2 cosine x quantity squared minus 5 cosine x plus 2. When is it equal to 0? Pi over 3, 5 pi over 3, 7 pi over 3, there we go. Just pi over 3 and negative pi over 3 plus 2 pi k. Wonderful. All right, we're solving trig equations. We're getting progressively more challenging. Hopefully you're seeing all these different types of equations and saying to yourself, I think I can do that. If you're struggling with it, if you're struggling to understand, please don't hesitate to shoot me an email or come to my office hours, get some help. Oh, I grabbed myself again. Well, Mrs. Contreras grabbed me. I did not place that there at the beginning to grab myself. That would be ridiculous. Ah, Mrs. Contreras grabbed me again. Anyways, cosine x is equal to 1 plus sine x. Okay. Okay. Take a second to think about this one. This might be a good spot to hit pause and then try the problem. Cosine x is equal to 1 plus sine x. Here's the problem, is I need to get a trig function by itself on the left-hand side. And I have two trig functions. And now, like, up here I have two trig functions, yeah. But I was able to factor and then use the zero product property. Get one trig function on the side by itself. Here I was able to factor and get one trig function on each side of the equation by itself. One trig function. One trig function. Let me jump back down to where we are. I have two trig functions and I can't factor. Is there a relationship between cosine x and sine x? Where I can get one type of function, sine x or cosine x, but not both. Watch this. I'm going to do this problem in 3, 2, 1. Let's square both sides. Throw back to the first unit where we were solving radical equations. Cosine squared x, 1. Let me just go ahead and do that just for consistency's sake. 1 plus sine x squared, quantity squared, is 1, plus 2 sine x plus sine squared x. Not bad. Cosine squared x, that's 1 minus sine squared x. That's a Pythagorean identity. Equals 1 plus 2 sine x. Oh, it's going to get a little bit easier. I'm excited. The ones cancel. Negative sine x squared is equal to, I don't need that plus anymore, 2 sine x plus sine, there should be a square there. Sorry about that. I'm going to add the sine squared x to both sides and get 2 sine x plus 2 sine squared x. There it is. Factor time. I think I can factor out 2 sine x out of both. 1 plus sine x. Yeah. There it is. Let me just double check I haven't made any mistakes. 2 sine x times 1 is 2 sine x. 2 sine x times sine x is 2 sine squared x. Cool. Alrighty. Let's go ahead and set these two things equal to 0. 2 sine x equals 0. Sine x equals 0. Divide by sides by 2. It gets us nowhere. When is sine x 0? Let me just think about it on the unit circle. When is the y coordinate 0? That is at 0 and pi. And then 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. So this is just pi k. 0 plus pi k. That's kind of nice. Right? The y coordinate is 0 there and there. 0, 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, etc. 1 plus sine x is equal to 0. When is sine x negative 1? I'm just going to use the same grid over here. When is the y coordinate negative 1? That's at 3 pi over 2 plus 2 pi k. All right, not plus pi k, because the y coordinate plus pi is 1, not negative 1. We need negative 1. There's only one place between 0 and 2 pi where the y coordinate's negative 1. 1 and negative 1 are unique that way. All the other coordinates happen twice. There are your answers. Pi k and 3 pi over 2 plus 2 pi k. All right, cool. We got one left. Let's do it in a new color. Let's do it in purple. Purple to close this video out. All right. We solved some basic stuff. We solved some stuff with arguments that were not just x, and we have that happening here. We can deal with it. We know what to do. We just set it equal to the place on the unit circle, and then continue on from there. So we're going to have to divide by 3. Then we did some factoring. I think factoring is going to play a role here. And I think at this point we're just combining all that stuff. Oh wait, we have a cotangent squared and a cosecant squared. That we need to deal with that. Cotangent and cosecant are related by the Pythagorean identity. Let's do it. Cotangent squared x plus 1 is equal to cosecant squared x. Nothing says I can't just replace that x with a 3x. So if that's the case, then cotangent squared x, or in this case, once again, cotangent squared 3x is equal to cotangent squared 3x minus cosecant squared 3x minus 1. Let's go ahead and do some replacing. It's going to get a little bit messy, but that's why we've been practicing all year. 3x minus 1 plus 7 cosecant 3x equals 4. This is just the previous problem with some other nasty stuff. I hope it factors. I really hope it factors. I can't remember. This one factors, everyone. 6 cosecant squared 3x minus 6, we're distributing, plus 7 cosecant 3x equals 4. Let's subtract that 4. We're going to get 6 cosecant squared 3x plus 7 cosecant 3x is equal to, oh no, sorry, not equal to. We're going to subtract 4 on both sides. Minus 10 is equal to 0. Let me scroll down a little bit, give myself some more room. Hopefully, this is enough room. All right, we need a factor. Oh, you know what I want to do? I'm going to do u substitution real quick, just to make it look a little bit cleaner. This is totally optional. But I'm going to set u equal to cosecant squared 3x, which makes this 6 u squared. Oh, no, I'm making u. Just cosecant 3x. Because I'm going to square the u. 7u minus 10 equals 0. I have really high hopes, guys. I really hope this factors. 1, 6, 2, 3, 3, 2, 6, 1. 1, 10, 2, 5. No need to alternate. I alternated on the left-hand side. We need to get 7. 10 and 6 does not give me 7. 20 and 3 does not give me 7. 30 and 2 does not give me, and 60 definitely not. So it's not going to be this. Let's see. 5 and 12. I think 5 and 12 is going to give us 7, because 12 minus 5 is 7. And we have a negative here, so we're going to have an opposite sign. I believe that's it. 1 and 2, 6 and 5. So we have a u and a 2, and a 6 and a 5. 6u and a 5. Let's make sure we get to 7. We want the number larger to be positive and then subtract down to the 7. So we want a plus 12u minus 5u gives me 7u. There we go. Ooh, this is not that pretty. Cosecant 3x. Remember, we're replacing the u with cosecant again. Cosecant 3x plus 2 is equal to 0. And 6 cosecant 3x, I'm sorry guys, 3x minus 5 is equal to 0. All right, you know, I am going to go ahead and add myself a page. Because I know over here, where I am, and Mrs. Contreras, I can't really write on top of that. It'll disappear. All right. Cosecant 3x plus 2 is equal to 0. And 6 cosecant 3x minus 5 is equal to 0. I am super happy. Here's why. Left-hand side, let's deal with it real quick. Cosecant 3x. I'm super happy about this side. It's like a little purple sun. Equals -2. Now there's two options here. We can think about where cosecant is -2 on the unit circle. But I'd rather just reciprocate and write, since sine and cosecant are reciprocals, sine 3x is equal to -1/2. I think about sine and cosine a little bit better than I think about cosecant. It's just my preference. So when is sine -1/2? We already dealt with this earlier. Sine is -1/2 at -π/6 or 11π/6 and 7π/6. 7π/6 plus 2πk. I'm actually going to do two equations. 3x is equal to 11π/6 plus 2πk. Why not? I mean, I could do it in one equation, but I'd rather just do two. And we need a number that when multiplied by 3 gives us 7π/6 plus 2πk, thus giving sine -1/2, thus giving cosecant -2. And then so on and so forth back to the original equation. That's why algebra works. We're doing everything in reverse. To do that, we just divide by 3. So 7π/18. 7/6 divided by 3 gives us 7/18. Divided by 3. Divided by 3. We're also dividing that 2π by 3 as well, though. 2π/3k. Then over here, divide by 3, we're going to get 11π/18 plus, once again, 2π/3k. All right, this thing I was super happy about. Add 5. Divide by 6. Cosecant 3x is equal to 5/6. When is cosecant 5/6? There's two ways to think about this. When is cosecant 3x equal to 5/6, or when is sine 3x 6/5? Think about the graphs. You could think about either graph too, to be honest, since we've practiced graphing both. Just trying to do a new color. Here's the cosecant graph. Think about its range. Here's the sine graph. Think about its range. -1 to 1. Here, it's outside of -1 to 1. 5/6 is right here. Cosecant never gets to 5/6. Similarly, 6/5 is right up here. Sine never gets to 6/5. Once again, the answer to this does not exist. These are our only two answers. Well then, what do we do if it did equal something valid, though? That's for next time. That is for next time. We solved trig equations using inverses today. Next time, we're going to solve trig equations with inverses with unfriendly solutions. So, dread that day. But bask in these problems. These problems were nice. They were doable. They were not that bad. I hope that you feel good about these. Just a quick recap. I know I've done a few recaps today. 2 sine x plus 1 is equal to 0. We isolated the function, the trig function, and then used inverse trig. Sine 2x minus 1, we isolated the trig function. Our argument was not x, but how do we compensate? We just continue on as if it was our variable and then divide by 2. Here, we had to factor a little bit. The big thing we learned in this one was don't divide by our variable. We would have lost information. If we divided by tan x plus 1, we would have gotten 2 sine x is equal to 1, which is valid. That's this right here. But we would have lost 3π/4 plus pi k. We looked at the graph. They intersected at 3π/4. We can't lose that answer. Down on number 4, we had to do a little bit of factoring. That was kind of cool. Getting 2 equations that we had them both solve, and the one on the right did not exist. That was nice. Plus or minus. That was a little tidbit that we talked about when solving cosine. Just do plus or minus. Don't worry about trying to think about the other answer. We got crabbed by Mrs. Contreras, even though she's not here. But in this problem, we had to square. That was nasty. And then down to number 6, a lot of more nasty stuff happened. There's one thing that we didn't talk about in this problem that we'll definitely address in the next video. But I want you to think about it. It has to do with this operation, squaring both sides. But I'll leave that for next time. Hopefully this video didn't go too long. We solved a bunch of equations. And then you're going to get the practice in class solving your own equations. You'll have more than 6. You're going to have a lot of practice. And if you want more, just let me know. And I got more practice problems. I got practice problems for days. All right, let's close this one out. Have a good one, everyone. I'm here back at the end. I made a mistake, and I need to address it now so that no one is super confused later. I'm back here on number 5. And one of my answers is actually not correct. Think about it. Pi k, 3 pi over 2. Let's plug them in real quick. Cosine of, let's do 3 pi over 2 first. 3 pi over 2 is equal to 1 plus sine 3 pi over 2. And actually, let me, just for the sake of this, let me go ahead and move Mrs. Contreras. There we go. All right, so you guys can see this. Cosine of 3 pi over 2. That is the x-coordinate 3 pi over 2, that's 0. 1 plus sine 3 pi over 2, that's negative 1. 0 equals 0, check. That's good. Let me go ahead and move the crab too. You know what? I'm going to crab Mr. Contreras by putting this crab over here underneath Mrs. Contreras. All right, so cosine 3 pi over 2, that works. 3 pi over 2 works. Pi, let's see if pi works. Cosine of pi is negative 1, x-coordinate at pi. 1 plus sine of pi is the y-coordinate, 0. Negative 1 does not equal 0. Pi doesn't work. That comes from that squaring. I know I said that would come next time, but I couldn't close out the video with something that was not factual. However, there's a problem because cosine is giving negative 1. If I plug in 2 pi, sine is still 0. I'm going to get 1 plus 0 is equal to cosine of 2 pi, that's 1. 1 equals 1. So the actual answer here is plus 2 pi k. We got an incorrect answer because we squared both sides of the initial equation, which is a non-reversible move. That's why we've been talking about it all year. That's why the square function doesn't have an answer. That's why we restrict non-one-to-one functions to become one-to-one to construct inverses. We need to be careful. I need to be more careful. And I apologize that I gave you guys the wrong answer here. I'm sure that some of you noticed and were freaking out when I moved on past 5 to do number 6. But there we go. This is the real closing out. I had to double check and make sure this answer was right and it was wrong. And that is something that's allowed to. You're allowed to do that. You're allowed to get things wrong, and then fix your answers. Yeah, there's no reason to check our answers here because we never squared. That came squared. This came squared. There was no squaring there in the first place. So the operation of squaring caused us to develop an extraneous solution. All right. Have a good one, guys. Sorry about that. I will see you in class.